Welcome back to the Math Professors, and today we're going to do some trig integrals. In this specific case, integrating products of powers of the sine and the cosine function. So here's our goal. What I want to do is I want to integrate the sine raised to the m of x multiplied by the cosine raised to the n of x dx, and I want to do this for all powers of n and m and n. So really, what we're saying is that m and n are going to be, integers. So these are going to be, in the integers. So what we're going to do in order to do this is kind of assume that one of these powers are odd. So let's let m be an odd value, odd number, which means that this can be written as some 2k plus 1. So an even number plus 1. So what I want to do is I want to be able to essentially work with that sine function. So I'll do a regular example, but let me just work on this sine piece of the 2k plus 1 and show you what I'm really trying to pull off here. So what we're going to have is we're going to have the sine to the 2k plus 1 power to the x. Now, I can rewrite this as the sine of 2k to the x multiplied by the sine to the 1 of x. So what I know is when you multiply things with the same base, you just add their powers, and since really there's a 1 there, then that's why that's the sine to the 2k plus 1. Now that this is an even power, what I would like to do is I like to write this as the sine squared of x raised to the k power multiplied by this, the sine of x still left over. So now that I have the sine squared to the k, we're almost done. I can take the sine squared and use the Pythagorean theorem, which says that the sine squared of x plus cosine squared of x is equal to 1, or solving it for the sine squared. So the sine squared of x is the same thing as 1 minus the cosine squared of x. So this is the same thing as 1 minus the cosine squared of x raised to the k power times the sine of x. Oh my gosh. But okay, so once you get used to doing this method a couple times, it gets really straightforward. And the first time you see it, you're like, whoa. So what this is going to allow us to do is really kind of make a u substitution here. So what I know is I'm technically integrating this, and I still have a cosine of n x dx over here. So integral cosine n x cosine n x cosine n x dx dx dx. So once we have this form, what we know is that I have a bunch of cosines to a power, and then I have this sine of x d of x left over, this product of the sine of x left over. What this will allow me to do is I can make u equal to, well, basically all these cosines I see. Then that'll make du equal to, well, the derivative of the cosine is negative sine, so this is going to be minus the sine of x dx. Or, multiplying both sides by -1, we can say negative u is equal to the sine of x d of x. So really now this thing just becomes a bunch of u powers. So this would be the integral of 1 minus u squared to the k power. This is u to the n power, and then the sine of x dx becomes a negative du. Okay. Now I'm gonna not finish off the integral of this generalized thing, because what I know is this 1 minus u squared to the k power. Well, it depends on k how big this thing is. If k is just equal to 1, this is just going to be 1 minus u squared times u to the n, and I can just distribute. But if k is a bigger number, say 2, I'm going to have to, I'm going to FOIL the binomial. 3, 4, 5, using the binomial theorem, you can multiply those things out to be very large. So essentially what I have is this can be expanded to some polynomial. So really what I'm trying to tell you is that this technically has some polynomial form, in terms of u. Now, when you're done integrating in terms of u, you have to unsubstitute, so turn all your u's back into cosines. So really what this is going to look like is a bunch of, cosines to a power, like a polynomial evaluated at the cosine function, or a composition of a polynomial in the cosine function. All right, let me put this into place. So I'll pause this, I'll do an example, and then you can see how this works. All right, so here's our example. We're going to integrate the sine to the 5th of x times the cosine squared of x dx, and we're going to follow the odd powers. So I'll do an odd power on the cosine next time to show you how this works. Or you can do an odd power on both, but really just kind of follow the odd powers. So the sine function can be written as, let's do it here. So this is the integral of the sine of 4x times the sine of x times the cosine squared of x dx. So what I've done is I've pulled off the largest even power to this. This is your 2k plus 1, so 2 times 2. So which means I can rewrite this as the sine squared of x raised to the second power times the sine of x times that cosine squared of x dx. Now that I have this as the sine squared, I can write it as 1 minus cosine squared. So this is going to be equal to the integral of 1 minus the cosine squared of x squared times the sine of x times the cosine squared of x dx. And now what I can do is I can make a u substitution. I see a bunch of cosines, and then I see a sine of x d of x. Actually, the important thing is the reason why we're pulling off that single sine function is because this is going to be my du essentially, like really a multiple of du, right? Negative du in this case, because the cosine, the derivative of the cosine. So if u is equal to the cosine of x, then minus du is going to be equal to the sine of x dx. Well, derivative of the cosine is negative sine, so minus du. Okay, so making our substitution. So this is going to be 1 minus u squared squared, so the integral of 1 minus u squared all squared. This is going to be also times u squared. Sine of x dx is going to be negative du, so this is now nothing more than really polynomial in terms of u. I have to square that binomial and then eventually distribute this u squared over that trinomial. So this is going to be equal to negative the integral of 1 times 1 is 1. This is going to be minus 2u squared plus u to the 4th times that u squared du. So that's that binomial expansion. And then I'm going to distribute the u squared into here. So this is going to be equal to negative the integral of u squared minus 2u to the 4th plus u to the 6th du. And now what we know about this is, again, like I said, this is polynomial form, so we just integrate. So this is going to be minus u cubed over 3. Minus a minus is plus 2u to the 5th over 5. Minus a minus is going to be minus u to the 7th over 7 plus c. And then we just unsubstitute. Your u is going to be your cosine function. So this is, to finish this off, is minus, the cosine cubed of x over 3. Plus, this is 2 cosine to the 5th of x over 5 minus cosine to the 7th of x all over 7 plus c. All right, so now let's make the cosine an odd, and actually we'll make them both an odd. It really doesn't matter. We really just kind of go after the odd power. So it doesn't really matter what one you go after. You'll get what one you do, you're going to get in terms of well, if you go after we went after the sine. This is now in terms of cosine because the sine squared turned into 1 minus cosine squared. If you go after the odd cosines, these are all going to say sines instead. But again, this Pythagorean theorem from here to here will show that I can rewrite these kind of in terms of the other one. Okay, so let's pause this. I'll do another example. All right, so here's our example. What I'm going to do is we have to go after the odd power because we have to use that u substitution. So I know that cosine cubed, this is going to be the integral to the sine to the 8th of x times cosine squared of x times the cosine of x dx. Now before I had a fifth, so this was squared, but this is already in the squared form, so we've already, we finished that method. We just turned that squared into 1 minus sine squared. So this is the integral of the sine to the 8th of x times 1 minus sine squared of x times cosine of x dx. And then we just use our u substitution. So, u is going to be equal to, notice all these signs, so this is going to be the sine of x, which means du is going to be equal to the cosine of x dx. So this is now going to integrate, well, this is going to substitute into u to the 8th times 1 minus u squared, simply du. Again, this is going to be a polynomial form. So this is going to be the integral of u to the 8th minus u to the 10th du. So integrating these things, we're going to have u to the 9 over 9 minus u to the 11th over 11 plus c. And then when we unsubstitute, we're going to turn these all into the u's, which are sines. So this is going to be the sine to the 9th of x over 9 minus the sine to the 11th of x over 11 plus c. So what happens if these powers are even powers? What do you do then? So I'll pause it. I'll show the trig identities we're going to need. All right, so here's our example. So we're going to integrate, these things as far as even powers, and what we have to do is we're going to have to use these identities. So what I know is the sine squared can be written as this, and the cosine squared can be written as this. So this is going to be equal to the integral of 1 minus the cosine of 2x over 2 times 1 plus the cosine of 2x over 2. I can factor out that 1/4 integral, and then I can multiply those two binomials. So outside and inside will cancel. So this is going to be 1 minus the cosine squared of 2x. Now again, what I've noticed is that I have another even power. I can integrate 1, which is going to be x, but integrating this thing, I'm going to have to use this. Now, if this says 2x, just doing a substitution, if this is 2x, this would also be 2x here in the x. So if this is 2x, this is 2 times 2x, which would be 4x. So this is going to be equal to, 1/4 times the integral of 1 minus, this is going to be 1 plus the cosine of 4x all over 2 still. So remember, this is only turned into a 4x dx. So now we can integrate these things. So this is going to be 1/4. Integral of 1 is going to be x. I can pull out that 1/2, so that minus 1/2, and I can integrate the top, which will also be x. Then integrating the cosine of 4x is going to be plus the sine of 4x all over 4, and then you'll close all this thing plus c. So, I can distribute this through and make it look a little bit nicer. So this is going to be equal to, x over 4 minus x over 2. That's not right. X over 4, this is going to be minus x over 8. 4 times 2. And when I distribute this here, this is going to be the sine of 4x over 8 times another 4 is going to be 32 with that minus. So minus the sine of 4x all over 32 plus c. And that is our antiderivative. So without doing a lot more examples here, is what happens if this was like 4th power and this is squared power and so on. So I'm not going to integrate it. You guys can distribute it. You can do that at home. But if this is a 4x, now what I know is that this is the sine squared. So that means, this is going to be that thing to the squared power. So, the expansion is going to become much more messy, okay? But it still comes down to, using these identities when these things are even, okay? So if one of them are odd, you use the previous method. If both of them are even, then you use this method. And that finishes the video. So again, please consider liking and subscribing. Thank you.